Now, if you remember, which you won't, but if you do, from the last lecture, we were looking at the idea of games of imperfect information, and we had a little card game that we did, okay? And I threw up some text on the overhead, got you to draw a little game tree, which we're gonna look at, and in one of the corner of the handout, there's a little sketch of the game tree and a payoff matrix that we didn't actually construct. Okay, I'm sorry the reproduction didn't come out too well in your the handout that you have, but you'll be able to get it from the rest from the overheads here. So we're going to have just to do a little review to kind of catch up with the concept of a game of imperfect information and using the idea of information sets, and then I want to go through fairly quickly 4 to 5 ideas. Okay, the idea of how to think about uncertainty in a game of strategic interaction. Okay, and so far when we've been trying to figure out how people look at various kind of games, what we've been doing is working with a Nash equilibrium concept. Okay, we have some payoffs. We have that structure. You know, who are the players? What can they do? What's the information? What are their payoffs? And then we try and work through, and we're trying to figure out what do we expect to happen. Well, we work through this Nash equilibrium idea, and that's what sets our beliefs about what we expect to happen. The strategies one player expects to play, the strategies another player expects to play, and everybody kind of works through the same kind of analysis, and we come up with these Nash equilibrium ideas which set people's expectations about what's going to happen in the game. Now, an interesting thing about these expectations or beliefs is that we didn't really do any statistics to figure out, oh, what's going to happen. We just sort of looked at people's incentives in the games, okay? And we use that best response analysis to come up with an idea of, well, you know, would they do this or would they do that? I don't really know, but if I think about it, I could work out what their best responses are, what their incentives are. They can work out my incentives are. We put those two together and we come up with this mutually consistent best responses or mutually consistent incentives, if you like, which we call Nash equilibria. Now, the only uncertainty we really, other than the fact that it's difficult to actually calculate these things sometimes, the only uncertainty we had was if there were multiple Nash equilibria, so we didn't know which one was going to happen. And that's an important idea, strategic interaction. Remember, we looked at the minimum effort coordination game where we had multiple equilibria. We wanted people to work hard to make a joint output, but it might be difficult to actually coordinate on doing the tasks that bring us the greatest output. Okay? And that arose because of the multiple equilibria. But now we're going to look at a different kind of game, which has what we call imperfect information. Now, I just want to remind you of what a game of perfect information is. When we have our game tree, and people are moving through the game tree, looking back, seeing the full history of play, if they can see everything, directly observe that full history of play, okay, so you can always tell precisely where you are in the game tree, that's a game of perfect information. Okay? A game of imperfect information means some players, sometimes, at some point in the game tree, when they have to make a decision, they don't know everything. Okay? There's some part of the game tree where they're not sure where they're at. Okay? And so we're going to call that a game of imperfect information. And we have to try to work out, well, if you don't really know where you're at in the game tree, so you don't really know what's going to happen after you make a choice, how do you work out what your payoffs are? Okay? And there's this thinking about uncertainty, about uncertain payoffs we have, there's two key ideas. There's the idea of belief. Okay? What do you believe when you have to make your choice? And then there's the idea of value. Given that you don't really know what's going to happen, how do you put a valuation on something when you don't know what's going to happen? Well, intuitively, you actually all do a pretty good job at valuing things that you don't know. So, for example, you took this course, right? You took a bunch of other courses. You went to university. You don't know what's going to happen, but you made a choice, okay? And you kind of looked at various pros and cons of the decisions you had, and you weren't sure exactly what's going to happen, but you can come up with, okay, this is something I'm going to do. I could have done something else. I'm doing this, but you still don't know what's going to happen, okay? Now, what we're going to do is we use the card game example because it's got a nice description of the uncertainties that face you. It's like a club or a spade was coming out of that deck of cards, okay? And then we want to step back from that and say, well, usually we don't know all those things quite as well as we'd like to, What kind of a deck of cards do we have here? Is Fountain, put in some different color cards. As do we really have 52? Maybe it's not cards at all. Maybe it's the weather, or the exchange rate is up, or the library's closed the day you go to study for your exam, or you forgot your notes, or all kinds of things. These things could happen, which could create some uncertainty. Okay, so we're going to spend a little bit of time thinking about this notion of uncertain payoffs. At the end of the day, we're going to come up with a number, just like we did before, and you always have to ask, what's that number mean when we're thinking about payoffs? But that one number will summarize, if you like, the way people look at uncertainty in a game of strategic interaction. Those numbers have to do with a concept called probability, which some of you will be familiar with because you've taken some stats, and others won't be too familiar with, except that you kind of know ordinary language about probability. This is more likely than that. There's a chance of this, perhaps this. You're not really sure. Well, actually, the people that don't know any stats will probably find it a little bit easier than the people who do know stats when we're thinking about uncertainty in game theory. Because it helps to put aside those preconceptions that statistics gives you, that you got to do all these measurements and stuff like that to be able to figure out what probabilities you might access. So we're going to look at the concept of probability, and once we figure out a notion of probability and figure out how we can use that idea of probability to characterize people's uncertain knowledge, or their uncertain belief, or their uncertain ignorance. Okay, I'm going to go back and forth between those terms. Okay, knowledge, belief, ignorance. When under uncertainty, they're really two sides of the same coin. Okay, when you know certain things, but you know that you don't know other things, that means that you kind of know that you're ignorant. Okay, and so the level of your ignorance is really the opposite side of the level of your knowledge. Keep that in mind. So the idea of our uncertainty here represents our knowledge, but it isn't sure knowledge, it's uncertain knowledge, which means it represents our ignorance. We're going to look at this idea of being averse to risk. Now, in many situations of strategic interaction, this is a really key element, okay? Like your selection of courses. Why didn't you take that physics course, which you've always wanted to do? Well, physics is tough, okay? I might fail. Or some other decision you make. You're thinking, well, I might succeed, I might fail, it might be good for me, it might be bad for me, but I'm a little bit risk averse here, okay? I don't want to, or maybe you're a risk seeker, okay? Why did you go off that cliff in your snowboard? Well, I was looking for thrills, okay? You knew what the risks were, but you decided to take them. So we want to think about the idea of probability as representing our beliefs, but there's more to uncertainty than just beliefs or ignorance. There's also what attitudes to risk do you have? Are you a risk seeker, or are you a risk avoider? Okay. Now let me go back to the this card game we had. You don't want to have to reread this text again. It was we drew a game tree, and it's probably easier to understand the nature of the card game through the game tree than this text. So we'll flick away from the text and go to the tree. Okay. If you remember, we introduced, in order to get a game theory representation of this card game, we introduced nature as a fictitious player. Okay. Now the idea is we had some clubs and we had some spades. We were shuffling those up. There was an equal amount of clubs and equal amount of spades in the deck, and the red player got to see their card whether it was a club or a spade. So we start off here to the left with nature choosing a club or choosing a spade. The red player at this node R1 could see that they had a club and could decide to either fold or to raise. Okay, and if they fold and they've got a club, they get 1, and the blue player loses 1. If they got a spade and they folded, then they lost the 1, and the blue player got the $1. Okay. On the other hand, the red player could decide to make this move of raising. Okay, and the idea is they could raise on a club, so we could have a club and they could raise. They got a spade and they could raise, and then we had the blue player having to make a choice, and we put this information set around these two nodes, B1 and B2, with the idea telling us that the blue player doesn't know which node that they're at when they have to make their choice. Okay, so the blue player can't say, oh, I saw the club, I saw the red guy raise, I have to make a choice, am I going to meet or am I going to pass? Well, in this case, if they've got a club, and I decide to meet, I'm getting -2, and if I decide to pass, I'm getting -1. So I don't want to lose 2. I'd rather only lose 1. I'm going to play it safe. I'll just because I'm going to guarantee myself a loss of 2 if I meet. So I'll just cut my losses and pass and just get my -1. Okay. On the other hand, if I saw they had a spade and the red player raised, then if I met that raise, I could get 2. Whereas up here, if I was meeting, I was getting -2. Okay, but we can't do that kind of reasoning because the blue player doesn't know whether it's a club or whether it's a spade. Okay, so they can't sort of say, oh, if it's a club, I'm going to do this. If it's a club, if it's a spade, I'm going to do that. They just have to make one choice. So we loop these two nodes together and think of it as one big node. They can either meet or they can pass. Okay, and let's have a look here. If blue decides to meet, then their payoff is going to be -2 or +2. Okay, it's going to be -2 if it's a club, or it's going to be +2 if it's a spade. And that's the idea of the way we can begin to think about uncertainty, is you make a choice, but the outcome isn't determined by your choice or by the other player's choice. There's some inherent uncertainty here, which is the draw of the card, okay? And we call that idea a contingency. Now, in this game, the contingencies are the draw of the card. In other strategic situations, the contingency would be different. You always got to think of what's the source of uncertainty. Well, in the previous games we were playing, the kind of source of uncertainty was, well, I don't really know what the other guy is going to do. It's a choice of somebody else. But we worked through our Nash equilibrium ideas, and we came up with some ideas how to resolve that. Okay? Well, in these kind of games, there's going to be, here's a draw of a card. Okay? It could be the exchange rate's up or the exchange rate's down. It could be the weather is good or the weather is bad. It could be Fountain sets a hard test or he sets an easy test. There's all kinds of sources of uncertainty, and those will be one way of thinking about uncertainty is, well, it sort of depends, okay? If it's this, I'll get this much, and if it's that, I'll get that much. Okay, so that's what we call a contingent payoff. And if we can set up a payoff table. So this is the diagram that I have for you that analyzes this sequential game as if it were a simultaneous game. Now, just for the moment, what I'm going to do is, go on in, there's lots of seats here. What we're going to try and do is think of this sequential game on the left-hand side in the game tree and think of the strategies of the players, put the strategies together in the payoff table, and see what we get. Okay? So the first thing we do is we work out the strategies. Well, the blue player only has 2 strategies. 2, okay? Because they can either meet or they can pass. Then the idea is that they have to make one choice at this information set. They can't say, oh, at B1 I can meet, and at B2 I could meet. At B1 I can meet, at B2 I could pass. They're not going to be able to make their strategies depend on what node they're at. The only thing they can do is when they get to this information set, they can decide to meet or pass. So M and P are the strategies of the blue player. What about the red player? Well, the red player finds himself in 2 situations in the game. They can be at node R1 where they get a club. They can be at node R2 where they get a spade. Okay, so the red player has 4 strategies. Remember, there's 2 situations they're in, and there's 2 things they can do in each situation. What are those 4 strategies? Well, you could say, well, if I got a club, I could fold, and if I got a spade, I could fold. That's always fold. So that's what I put up here in the first row, 2 F's for fold. And on the left-hand side, I'm saying, excuse me. If it's a club, I'm going to fold. If it's a spade, I'm going to fold. Okay. What's another strategy? Well, supposing you get a club, you can fold, but if you get a spade, you can raise. So that's an F here and an R there. So we've got an F and an R. And similarly, we had an R and an F and an R and an R. The 4 logically possible strategies. Right? So the red player has 4 strategies. The blue player has 2 strategies. So we have a payoff table that's 4 by 2. Now, whenever we've looked at a payoff table, a payoff matrix before, we've always just had one pair of numbers in here, not a bunch of numbers like this. So let's see what I'm doing here when I'm filling in all of these boxes. Supposing we take the red player strategy of always folding, fold, and fold. Okay? And we match it up against the blue player strategy of meeting. I think, well, it doesn't matter, does it? It doesn't matter if the red player always folds, then the payoffs are going to be a red 1 and a -1 if it's a club, and a -1 for the red and a +1 for the blue if it's a spade. But from the standpoint of the red player, their payoffs are going to be either 1 or -1. Got that? If they play the strategy of always folding. 1 if a club, -1 if a spade. So I put this here. 1 if a club, -1 if a spade. What about for the blue player? Well, if they decide to meet and the red player decides to fold all the time, their choice isn't going to matter. But what they're going to get is -1 if a club, 1 if a spade. So we've got -1 if a club, 1 if a spade. And so what I've done is throughout all of the cells here, I've gone through and I've put in the various combinations. So let's just pick one at random here, like this, the strategy of on the third row, raising if you've got a club. So you're going to come along and go with a club, and if I raise, the red player raises. This is the choice that we made. And if I've got a spade, I'm going to fold, so we're going to be up over here. Okay. Now let's match that strategy up with, let's take the meat strategy. Okay. So what do we get? Well, if it's a club and we're raising and the blue player meets, the red player is going to get 2. If it's a spade and the red player is folding, he's going to get -1. So I put in the 2 and the -1. Okay. So the idea is that every one of these cells holds a contingent payoff. Okay. The contingent payoffs for the red player are on the left-hand side, 2 and -1, 2 if a club, -1 if a spade, 1 if a club, -1 if a spade. For the blue player, -1 if a club, 1 if a spade. Now, I've gone through this for about 2 or 3 years now, so I think all the numbers are right. But you should go through and check out, could I, from that left-hand side payoff sequential game, the game tree, could you construct that payoff table? Right. It's a little tedious. You got to work your way through it, be systematic. But remember, the entries now aren't just single numbers, because what we're entering in the payoff table is, oh, if a club, I get this. If a spade, I get that. If a club, I get this. If a spade, I get that. Okay, it's a contingent payoff. Now, that looks a bit messy, right? That doesn't look like anything we've added before. How do we analyze this kind of game? I mean, we've got the payoff table. We've got the player strategy. We're kind of looking for Nash equilibrium ideas, best responses. What should we do? Well, what we're going to do is simplify the table by saying the way that a player looks at whether their payoff is not, oh, I could get 1 or -1, I could get 1 or -2, I could get 2 or -1, I could get 2 or -2. What they're going to do is come up with a single number to represent that contingent payoff. And we're going to introduce the idea of a probability weighted average here. Okay, so I've just got rid of the game tree here, and I've got the same payoff table. Now, what I'm going to do is concentrate on the blue players -1 and 1. What's the -1 and 1? Well, it's like, oh, if it's a club, I lose 1. If it's a spade, I gain $1. If the red player always folds. Okay, so that's the blue player's payoff. Now, what we're going to do is, because we know, at least the way we set the game up, is that the probabilities or the chances of getting a club or a spade are 0.5. Just take that on faith right now. What does this idea of probability mean? Well, the number 0.5, if you look at we had 13 cards, or 26 cards, 13 clubs, 13 spades, half each. So probabilities we'll assess them as a half. And then what we're going to do is take a probability weighted average of the -1 and the 1. Okay. The probability, we're going to take an average number, which is halfway in between the 1 and the -1. Well, that turns out to be 0, right? Wherever we get a -1 and we've got a +1, if we're, here's 0, and if we go out to the right-hand side, +1, and if we go out to the left-hand side, -1, and we put equal weights on the -1 and the 1, we're going to end up right in the middle, which is at 0. Okay. So if the probabilities are 0.5 and 0.5, and if the numbers that we're averaging are -1 and 1, if we take a probability weighted average, we're going to end up in the middle. Okay. Now, later on, we're going to be calculating, well, trying to think about uncertainties where we're going to have numbers that are different than simple things like -1 and 100. It might be like 84 and 72, okay, or -72, and you got, how do I average those out? Well, you could do it if you had a calculator, but a nice easy way is to think, well, a probability-weighted average always lies along a straight line. Okay, just remember that concept. It's a nice geometric concept we'll come back to over and over again so we don't have to do the calculations. I put the number out here, which is 1, the number out here, which is -1, draw a straight line between them, and the probability-weighted average will lie along the straight line between them. Here it's halfway in between because I've got a 0.5 on each one of them. A 0.5 on the 1 and a 0.5 on the -1. If I had a 0.9 probability on the +1, I'd shift over here and my weighted average would be closer to 1. If I had my 0.9 probability on the -1, my average would be somewhere over there to the left. So we can use that straight line to represent kind of where the average is going to be. It's going to be towards one side or the other. Okay? Now, supposing I take all of the places where there's a -1 and a 1. There's one there. There's a -1 and a 1. What have I got? I got a -1 and a, whoops, I got a -1 and a 1. And I plunk in zeros. Well, so I had a red 1 and a -1. It doesn't really matter the color when I take the average, right? A red 1 and a -1, a red 1 and a -1. So all of those places, I'm going to put in zeros for the payoffs. Okay. Why am I doing that? Well, what we're trying to do is we're saying, look, we've got this game that people are playing against one another. There's some uncertainty in it, so they don't really know what's going to happen. The uncertainty here is described by their contingent payoffs. That is, if it's a club, they're going to get this, and if it's a spade, they're going to get that. But that's kind of messy to think about. So what we'll do is we'll summarize those contingent payoffs by taking a weighted average of the payoffs, and we'll put those numbers into the payoff matrix. Okay, so. At first, I just did all the 1s and the -1s, and I put zeros there. Okay, it makes it look a little bit more familiar, right? Instead of these contingent payoffs, we're saying, oh, the payoff to the blue player, if he plays M, and the red player, if they always fold, is a red 0, a blue 0. Okay. Now, remember, at the very beginning, I say, whenever you see these numbers in a payoff table, you always ask, what do they mean? Well, these numbers aren't describing what's going to happen to the game in the game, because if we wanted to describe the outcome of the game, we'd be saying, oh, well, if it's a club, the red player is going to get 1. If it's a spade, he's going to get -1, and the blue player is going to get -1 otherwise, and 1 if it's a spade. Okay, so that's the way we would describe what's going to happen. But we want to figure out what people's preferences are, okay, what their payoffs are, and so we put in these numbers, and we'd say, oh, the blue player assesses a 50-50 gamble on 1 and -1 as worth a 0. Okay, it's like, oh, I could get 1, I could get -1, but on average it's 0. So that probability-weighted average will be my assessment of this risk that I have. Okay. Similarly for the red player, they can get a 1 or a -1. Halfway in between is 0. So 0 is going to represent their assessment of that risky situation that they're in. Okay. Similarly for every one of these other cells, the zeros represent the individual agent's assessments of the risks that they face. Let me say that again. The numbers represent the assessments of the risks that they face. How do we do those assessments? Well, we just took probability-weighted averages. Okay, numbers that are in the middle. Now, there's we want to come back to that concept because you think, why are we doing this? You know, like, what do people just take probability-weighted averages of numbers to come up with risky assessments? Well, could be, could not be. Okay, depends what your attitudes towards risk are. We'll come back to it in a second. But for a moment, just stick with me. That we're thinking, okay, you could get 1, you could get -1, you could get 2, you could get -2, you could get 2 and -1. All these different numbers. We're just going to take a probability-weighted average of the number to find out a way of assessing the value of that gamble to the various players. So let's do it for the other numbers. Okay, so if we take a probability-weighted average of 1 and -2, where there's going to be a 0.5 probability on the 1 and a 0.5 probability on the -2, okay, that's going to be a little bit less than 0, isn't it? Right? Because we've got it going to the right of 0, 1, we're going to the left of 0, -2, but equal weights in each one, so it's going to shift it to the left a little bit. Okay? And similarly for every one of these other numbers, and so I went through and I calculated all the other numbers for you. Now again, just a little homework exercise. You know, try and take this final payoff table and go through and say, oh, if I had to do that, which I don't want to ask you to do, but if you had to do it, when you've got a calculator and you've got time and you're not under pressure on an exam, could I actually construct that payoff table? Okay. I mean, once you get a bunch of complicated numbers, it gets really hairy. But for simple numbers, I would hope that you could actually construct that payoff table. But it'd be very easy to get it wrong, right? Because it's simple to make a little arithmetic error in doing these averages. Now, again, what are these numbers? Well, let's look at just the blue numbers. We got some zeros, we got some minus ones, we got a 0.5, we got a minus 0.5, we got a minus 1. Well, think of those numbers that higher numbers are better and lower numbers are worse. Okay? So, for example, the blue 0.5 is the best outcome of them all for the blue player. Okay? Excuse me. And the worst one is a minus 1. Now, that doesn't mean that this minus 1 doesn't mean you're going to lose $1 for sure. What it actually means, well, let's take away and go underneath it. What it means is, well, this one it does mean $1 for sure. Okay, you're losing minus 1 if you've got a club, and you're using minus 1 if you've got a spade. Let's try the minus 0.5. What does that mean? Does that mean you're losing 50 cents for sure? Not really. Let's go back behind it. What you're losing is 50%. What you're getting if you play meat against a raise and a fold strategy of the red player, as a blue player, you're losing $2 if it's a club. You're getting $1 if it's a spade. Okay, so really your payoff is going to be either minus 2 or 1, but you assess that as worth minus 0.5. So it's a lower number than 0. So let's look at that. It's a lower number than 0. It's a worse outcome for you than 0. How does that work? Well, if you compare a minus 2, and a 1 with a minus 1 and a 1, the worst outcome here, minus 2, is much worse. Well, it's worse than that one there, right? So you'd expect this risky situation to be better than that risky situation because they got the same top prize, but this one's got a worse bottom prize. And that's what this averaging does. It helps kind of keeps that sort of intuitive kind of structure that this risky situation here, a minus 2 of a club, 1 of a spade, is worse than minus 1 of a club than 1 of a spade. Okay, so we plonk those numbers back in again. So, okay, you got the idea? We're going to take, when we have games of imperfect information, that will mean that the outcomes of games aren't sure for people, but what they can do is they can take probability weighted average of things to come up with a number which helps them assess the gamble. Okay? And then once we get that, we get our standard payoff matrix. So let's see what would happen. Let's do our best response analysis. 1, 2, 3. Put in your X's and O's. Okay, I'll put them all in here for you. If you go across the rows, the blue player, 0 and 0, 2 best responses. If you go across this row, for the blue player, 0.5 is better than minus 1. 0 is better than 0.5. 0 is better than minus 1. And similarly, up and down the columns, for the red player, if the blue player meets, 0.5 is the highest. Over here, 1 is the highest. 1 is the highest. We've got 2 best responses. You know, we crunch through our best responses, and you think, there's no Nash equilibria in the pure strategies in this game. Okay, it's one of those games where I'm looking for a Nash equilibria, but I can't find one. Okay, if the red player decides to raise when he's got a club and fold when he's got a spade, then the best thing to do is for the blue player to pass. But if the blue player passes, then the best thing to do for the red player is to either go to this strategy here, fold if he raises, and this strategy here, fold if the club, raise with a spade, or the other one, always raise, okay, because those will give you a payoff of 1. But if you're going to do either one of those, then the blue player's best strategy is then to meet, in which case your best strategy is to do this one here, in which case his best strategy, and you just go around and around in circles. Okay? So the idea here is that if we do our best response analysis on this card game, we don't have a Nash equilibria. And we'll see, like tomorrow, when we look at the concept of the mixed strategies, there will be a Nash equilibria in this game, but it won't be one in pure strategies. We have to introduce an idea of kind of bluffing or uncertainty or surprise, which gets us a different concept of a Nash equilibria. It's called a mixed strategy Nash equilibria. Okay? But for the moment, forget about solving the game. Just saying, well, we've looked at it the best we can now, and we find a game which there is no definite Nash equilibria in this game. Okay? So there's no mutually consistent best responses in terms of these, what we call these pure strategies for each player. Okay. Got that idea? Where we started with a sequential game with imperfect information. Okay? And we traced it out. Then to analyze the game, we said, well, how do we work with this thing? Well, we can work out the player's strategies. We work out those strategies, and we analyze it the same way we analyze other sequential games, as if they were simultaneous. Well, they're not sequential. They're not simultaneous games, but we can analyze them as if they're sequential games by looking at the full strategies for each of the players. We come up with a payoff matrix. We get this complicated payoff matrix with these uncertainties in it, which depend on contingencies, which depend on clubs and spades in this case, but we know the probabilities of clubs and spades, so we can take the probability weighted averages, and we come up with this final payoff matrix here. Okay. Now, the key thing for an exam for you guys is really to be able to work with something like this. Okay, but remember that in order to analyze these sequential games with imperfect information, you've got to take account of all of their strategies. And their strategies won't tell you a unique outcome. So we're going to have to do this probability weighted average kind of thing. So let's have a look at why we're doing the probability weighted average thing. In the card game, we had a probability weighted average of simple numbers, like a payoff of 1 or a loss of 1. Okay? And if you take 50-50, that gives you right in the middle of 0. Just think about whether you really would like to do that. Supposing I'm sitting here and I give you $50 for sure. Well, not bad, right? $50. I'm sorry we can't play this one for real, but I don't have $50 to give you. Okay, and so I think, well, okay, $50 for sure. That's whether, let's say, whether you got a club or whether you've got a spade. And you think, I like that $50, right? Now, what if we introduce a gamble on a club and a spade, 50-50, which is 80 and 20. Now, if you take a probability weighted average of 80 and 20, half on 80, that's 0.5 times 80 is 40. 0.5 times 20 is 10. So the probability weighted average is going to be 40 plus 10 is 50. What would you rather have? $50 in the hand, or on the draw of a card, $80 or 20? I think, pardon? 50 in the hand would be nice, wouldn't it? Yeah. What if it wasn't $50? What if it was just 5 cents? Well, let's make it 50 cents, because we don't deal with 8-cent pieces anymore. Okay, so 50 cents or 80 cents. What would you do the same then, or would you take the punt? 50 cents in the hand? Probably take the punt, because it's just, I mean, what's 50 cents or 80 cents, right? I mean, it's like you got a chance at 80 cents, you could have got 20. 50 cents is hardly anything anyhow. But when it's $50, you sort of think, oh, okay, 20. You know, I mean, some people might take the punt. A few years back, I taught our third-year theory class. We were kind of working through some of these risk attitudes, and there was a guy in the class who was he had made a lot of money betting on the TAB. And every time there was a gamble like this, he was always taking the gamble rather than the certainty. Okay, and first place, he had a lot of money. Okay, and the second place is, given that he had a lot of money, he was willing to take a lot of risk. I mean, it's like, okay, if you already have a lot of money, you're sitting there with a few $100s in your pocket, and you're thinking, another 80, that'd be nice. 20, I'll do it. Well, that's the idea of your risk attitude. It's not just looking at $50 for sure versus 20 or 80. Let's make it the spread a little bit wider. What if it was 90 and 10? Okay, then you think, oh wow, that 90 looks pretty good, right? But 10 looks pretty bad. Now, when you think of this kind of idea is quite important. multiply these numbers times 1,000. Think of it as your annual salary. Many years back, in the mid-'80s, I started the Apple user group with some guys from IT, and eventually it turned into a company called Magnum Mac, which is a Macintosh sort of company. I got out of the company in the early '90s, and one of the things I found out about myself is I'm not a risk taker. I just we had so many outstanding debts. And like you would have to pay cash up front in the States for everything you're buying, and you got people on credit over here, and our credit cards were maxed out. We may have 40, 50,000 debt in credit cards, and you think, how can you do that on credit cards? Exactly. It was very scary. But it was a risk. Just the whole thing. These guys who ran the company, they're multi-millionaires now. Okay, if I'd stayed there, I would have been pretty wealthy. On the other hand, I was risk averse enough to want to get out, and I felt better getting out because I didn't like those big risks. Okay, and it's the same with your salary job. Okay, you take a job, you get a salary, and work your way through it. Or you could go on a commission somewhere. Okay, and you get a low base payment and a low salary, and then you might get a commission, but you might not get anything. Okay, or you could start a small business, and you think, well, I could make some great gains, or I could have some huge losses. Okay? So that's the kind of thing we're thinking of sort of intuitively. Is like when you're looking at these payoffs and we're averaging them out, people who are risk averse kind of tend to like certain things rather than uncertain things. Now, I say tend, okay, because just because you're risk averse doesn't mean that you don't take risks. It's just that you prefer certainty, as long as it's good enough, to a risk. So, for example, if I was to say, okay, here's the gamble at 80 and 20, would you like that or $30 for sure? 50-50 gamble at 80 or 20, or $30 for sure. Can you just like what you're thinking? 20's not much worse than 30, but 80 is a lot more than 30, isn't it? Okay, let's think of it that way, okay? Because what we're doing is you're trying to figure out how would a rational, intelligent person think about different kinds of risky situations. So $30 for sure, or 80 or 20. Well, I could get a gain. What's 30 to 80 is 50, or I could get a loss of 10 relative to that 30. Okay, a gain of 50, that's big. The loss, pretty small. Okay, so if I sort of think of it that way, and I'm thinking, well, 50% chance at a big gain, 50% chance at a little loss, kind of on average, I expect to make a positive gain there. Okay, that's the way to think about it. Now, what happens is if you look at that, take that logic with these other gambles, what you could think of is, well, if I'm looking at 80 and 20, and I'm comparing it to 50, I could think, well, I've got a gain of 30 or a loss of 30. Okay. And matter of fact, it's an equal amount of gain and an equal amount of loss. Same probabilities of gain, the same probability of loss. Equal amount of gain, 30, equal amount of loss, that's the money loss. Okay, but if you're thinking salary, we're looking at 50,000. You got your student loan to pay, you got your mortgage, you got all these sort of debts. You go down to 20,000. You're in big trouble. You have 50, you can cruise along. If you had 80, it'd be fantastic, right? But you sort of think, well, the value to me of that extra 30 gain is good, but it's not as big as the loss of the 30 if I lose it. Okay, so that's you could sort of think of why do I prefer the certainty of 50? Well, I do like gains of plus 30. How much? Well, quite a bit. But I'm also taking the risk of getting a loss, and that loss is going to push me down to a low income, and I don't like that. I don't want to take that risk of that loss. Even though they're an equal monetary amount, they're not an equal value to me. Okay? And at the end of chapter 7, there's a discussion in the appendix about how you can scale these payoff numbers, looking at the idea of gain and the idea of loss. And so, under uncertainty, the way we'd like to represent payoffs is not just the expected monetary payoff, okay, but if you like, the expected payoff to you, what we call the expected utility payoff, which comes by thinking how much value or utility do I get from a gain in money as compared to a loss in money. Okay? Now, there's I put here a little graph, which I'm I'm just going to sketch up. It's supposing you think of, on the horizontal axis, you've got your money payoff, okay? And you think, oh, I like more money than less. No problem. Everybody, well, we'll assume everyone likes more money than less, or more of whatever the payoff medium is. But how much more? Okay, that's the idea. Well, what we call risk-neutral people, their utility of money goes up in a straight line. And the way to think of that is a $30 gain gives them the same extra amount of payoff, utility, as, sorry, I shouldn't say payoff. A $30 money payoff gives them the same extra utility payoff as a $30 loss. So we say their utility is linear. For risk-averse people, whatever their utility is of $50, an extra $30 of payoff gives them a little bit of an extra value, if you like, personal value, utility value. I'll put that up there like that. So the extra 30 gives a little bit extra value, utility value, but the loss of 30, or going here to the right, the loss of 30 gives a drop in utility that outweighs that. Okay, so if you scale the money payoffs by this red function, which the economists and game theorists call utility function, you're not going to have to do this for an exam or anything. It's just the concept of what payoff numbers should I use to represent people's attitudes towards risk in a game. Well, what I should try to do is figure out what their attitudes towards risk are. We'll use risk-neutral people a lot because it's easy to take probability-weighted averages of numbers. But it's an assumption. Remember, our models were if, then. Okay. Well, what we'll do with our payoff numbers when we come to the payoff matrix is we'll think of them, or think of the agents as being risk neutral. That is, what they do is they take probability weighted averages of their payoffs, so they would be indifferent between $50 for sure, or a 50-50 gamble at 20 and 80, or a 50-50 gamble at 10 and 90, or a 50-50 gamble at 0 and 100, because they all have the same expected payoff. Okay. Now it's a pretty tight assumption, because as that spread gets bigger and bigger, we would like to say we'd like to have people's risk attitudes tucked in there. If people are more risk averse, then assuming risk neutrality won't be the right way to model or think about their payoffs. Okay. Just tuck that in your head a second, because all I'm doing is asking you, how do you interpret those numbers in the payoff table? So if we go back to that payoff table, sorry, let me get this one here. If we go back to this payoff table, these numbers in the payoff table were supposed to represent the agent's preferences. Okay, and here the preferences now numbers are probability-weighted averages of things. Could be chocolate bars, could be money, it could be preference ranks, whatever those probability-weighted averages are. People have risk attitudes towards those things. Okay, so we want those numbers to reflect their risk attitudes as well. Now, okay, we talked about probability-weighted averages. And I just took the 0.5 probabilities from the card deck because I sort of assumed, well, everyone's going to think their probabilities of 0.5. But what's the probability of 0.5? Supposing you're thinking about your chances of passing the course. And you think, well, or it might be, you think, well, it's almost 100% chance I'm going to pass it. Well, in midterm, what about your chances of getting an A? What about your chances of getting a B? Okay, and it's not quite like drawing a deck or a card from a deck, is it? Well, if it is, you don't really know how the deck is stacked against you or for you. You're not sure what's going to happen. You could get that A. You could get that B. But if you want to come up with a number that represents your uncertainty, then you have to think a little bit deeper. Now, it turns out we're going to think of probabilities as a way of representing uncertainty. But there are three ways you're going to interpret these probability numbers that we're going to come up with. The first is called the formulas. These are the mathematical guys. And if you look at the appendix of Chapter 7, which you don't have to memorize for the exam, but I'd like you to read through it to get an idea, what are the laws of probability? Why do people even think about probability? Well, there are certain rules that you use logically and mathematically to come up with probabilities. Like, the probability of something has got to be greater than 0 and less than 1. Okay? And then if you have the probability of two events, you might ask, well, is it the sum of the probabilities, or is it the sum of the probabilities minus something? There's all kinds of little rules for probabilities. We don't have to get hung up on the ways of thinking about manipulating probabilities, but the formalist guys, they just say probabilities are numbers that have to satisfy certain rules. The second set of people are the what are called frequentists. Okay? Now, the frequentists, everybody accepts the mathematical formalist kind of logic, but they say, well, what does it really mean? Okay? And the frequentist guys say, well, look, when you say that probability is 0.5 from getting a club or a spade, it means that if we just repeated this game over and over and over and over and over and over again, and if Fountain really had put in 26 cards, which were 13 clubs and 13 spades, and if you really did shuffle those up very, very well each time, okay, then in the long run, you expect about half of them to be clubs and half to be spades, okay? So that's what a frequentist concept of probability is. Try to apply that concept to your passing the course. If you got a 50% chance of passing the course, 50% or better, and you think, well, yeah, I do, okay? You might put it at 0.6. Maybe even put it at 0.8. Where's the deck of cards? Where's the repeated times? Okay, I mean, this is a one shot for your standpoint. It's like this is this course. I didn't do it last year. Now I could come to you and I could say, okay, I've got stats going back 6 years on all the other people who passed my course. I could tell you that about 80% of the people pass the course and 20% of the people fail. But those are all kinds of people. I mean, there are people, there are people who are 60, there are people who are 18, there are people who have A pluses everywhere, and people who have E's everywhere. There are people, who, you can imagine all of the variety of people there are, and you're thinking, well, how do those things relate to me? Okay? So then we come up with the last idea, which is called the subjectivist idea, is that the probability, I mean, it isn't just mathematical, and it might be helped by having some counts or measurements and things like that, but it's really my personal belief. It's called a subjective probability. Now, the idea of the subjective probability is, say you were to say, well, my probability for passing this course is 80%. And I don't think it's as high as 90%, but I'm pretty sure it's higher than 50%. Okay? So the idea with the subjective probability is you can come up with a number. That number can be useful in terms of comparing with other numbers, like the 50%. It's better than a coin toss, and I'm going to pass the course. It's not a guaranteed thing, though, because I could fail. Okay, so I'm going to put the number around 0.8. It could be 0.9. It could be 0.7. Now, when we come tomorrow, what I'm going to do is I'll walk you through an example of how I think the sports betting bookies at the TAB establish probabilities for events like, the Crusaders playing against the Chiefs on the weekend, the All Blacks against South Africa, whatever sporting events that they're talking about, how they come up with their own subjective assessment of a probability. Now, one idea about that, it's just really, I think, really fundamental, is those guys, when they talk about probabilities, they back up their beliefs by being willing to bet on those numbers that they place out there. And that's where this idea of subjective probability becomes what we call operational, is when you specify a probability number, like 0.8, it's going to be a number just like the TAB. You'd be willing to make small bets on your passing the course at prices which reflect that 0.8 probability, and we'll see what those are tomorrow. Okay?